Good morning and good evening, folks. So is the Cisco team in this meeting now? Okay, seems not. Hey, Sachin. Hey, Sachin. Can you hear me? Hello?
Hey, hi.
Hey,
Hi, guys.
hey, Sachin. Hey, will you present or someone else from Cisco side? Not sure who will
Yeah,
present.
I'm the one who
Okay,
presents.
okay. I think you can share your screen. Then after people join, we can start.
Yeah,
Maybe 8-3. Usually people will join a little bit late, so let's give them several minutes.
yeah, sure.
I can see your screen.
Thanks. Yeah. So, so
Yeah, let's wait for several minutes. Then we can start. Okay. Good morning, good evening, folks. Welcome to the SONiC community meeting. In today's meeting, Cisco team will present the secure boot key management. So this is part of the secure boot, the whole end-to-end scenario, which plays a critical one. Thanks the Cisco team. And also, I would like to call the reviewer for these features. Previously, I know NVIDIA and Cisco contributed the secure boot, secure upgrade features. So we welcome others to contribute to the security boot related feature review. So if you want to be the reviewer, just leave your comments in the HLD or just ping me so I can help to add your GitHub ID. Okay, with that, I will hand over this to Sachin to present his HRD. Please go ahead, Sachin.
Thanks. Hi guys. This is Sachin Naik, and I am currently working in the Cisco, especially on this secure boot aspect. The secure boot. This is the PR I have opened recently. Yes, as I need reviews and the comments if there is any. Let me get into the HLD document. Okay, let's start with what is secure boot. SONiC already supports a secure boot, right? So NVIDIA has committed changes about that. The secure boot is a UEFI standard, and there is a specifications available. And the specification, I think, starts with the 2.3 onwards UEFI specification. They have defined how the secure boot is supposed to be implemented on the compute node, and how the keys are managed. Um, but the implementation may vary based on the UEFI firmware that we use or how we implement. But the core principle of the secure boot should be the adhere to the specification. So the secure boot basically helps, verifying the signed images. That means the images, whatever that loaded on the compute node, should be signed, and its integrity has to be checked before loading onto the system. That way, it prevents any unauthorized image to be loaded on the system, as well as it also does an integrity checks so that it can avoid any malware or any kind of a vulnerability in the early boot up of the system. So what is the requirement here? So we have implemented the secure boot in the SONiC already, right? So, but the platform owner, like in this case, whoever owns the SONiC hardware in their operational network, right? So the platform owner definitely wants to manage these keys according to their operational policy has been set on the hardware, right? So once the keys are there in the secure boot system, that cannot be stayed forever on the system. It has to be basically changed depending on the policies being set. Some platform owner wants to change these secure boot keys in the periodic manner, okay? Or some, if there is any compromise or a vulnerability or the secure boot keys got compromised, the system has to basically remove those keys or revoke those keys. To do that, there should be a interface available in the SONiC, to go and make the changes. Now, when we make the changes, it should be secure enough. That doesn't mean that actually anybody can get into the system and make these changes. That can be potentially threat for the system. That is why the UP Secure Boot specification defines some core principles behind it. Now, there may be many variation of implementation, but here, right, while writing this design, we looked into the standard, what the Linux normally provides, and what is the available in the open community. So we have taken a reference of OVMF. This is the Open Virtual Machine Firmware. that is available in the open community. They have implemented the UP secure boot. So we have referenced that one, and based on that, we added it. But for a SONiC purpose, this should be a very generic, and the platform implementation can vary depending on the what firmware they have used. But the general guidelines is that the system, the hardware supplier supposed to supply this specification or how to access all this manual to the platform owner, so that actually it has been implemented in the secure way. So the requirement here about the we don't talk about the secure boot itself, because secure boot is already being added, but we mainly focus on how the secure boot keys are managed in the system by the platform owner, right? Basically, they should be able to show the secure boot keys. It is like a dumping the keys from the system, and also they should be able to add, remove, or revoke the secure boot keys from the system. Now there is a one more, I think it's missed here, that is a creation of these UEFI keys, right? This normally happens outside of the system. Some vendor support has their own signing infrastructure or key production infrastructure, or there are standards available like OpenSSL tools and all. So here we referenced mostly on OpenSSL based. Thus, and most of the signing infrastructure should support the same similar OpenSSL model. So in the secure boot framework, so basically there are several component comes. So let's touch upon that. That we have in a UP firmware. As I mentioned, it's a a kind of a replacement of a traditional BIOS. And UEFI stands for universal extended firmware interface, kind of a flexible interface that that it provides to to manage the UEFI firmware itself or interact with the UEFI firmware itself, right? So in this case, we have mostly referenced the open virtual machine firmware that is basically used for KMO or a KVM virtual machines, and they have implemented the UEFI secure boot. When we talk about the UEFI secure boot, it involves several keys. Okay, like in this picture, this is what actually the specification also mentioned, that there should be a platform key, which is we call normally PK. It could be self-signed, or there will be a CA for that, and there will be a key exchange key, and a signature key list, and a forbidden key list. So the specification also defined the roles and responsibility of these keys. These keys basically act as in a hierarchical order. The platform key is being the platform owner's the root key, and it provides at most root of trust, and it has to be very secure. And we basically won't use this platform key very frequently. Okay, and it is a self-signed, or it can be a CA signed. So the platform keys, why do we need a platform key? The platform key basically say that in the secure boot world, right? So the hardware vendors may be different, the platform owner may be different, and the NOS vendor may be different. So, or they can be a same. So it can be any combinations, right? The hardware vendor, when he supplies the system, then it has to be the platform owner, whoever purchased the system should be own the platform. The PK kind of establish the trust relationship between the platform firmware and the platform owner. That way, um, the platform owner can own the device. Now, the PK enrollment ideally happens either in the early stage, like when it is manufactured, or when it is before supplied to the customer, or in the customer premises in the early boot state. It depends on the how the hardware vendor, platform vendor has an agreement. In a PC kind of a world, normally this is sent to the user without being locked, or sometimes it is locked with the password. And the BIOS UP firmware is kept in a certain mode, so that at that particular mode, the PK can be enrolled. So once the PK is enrolled, the system is basically, you can say that UP firmware has a man in the two different mode, user mode and setup mode. That's what OEMF does. That in a setup mode, it accepts the platform PK. Once the platform PK is enrolled, the system gets kind of locked. That means any modification after the PK's enrollment is required a certain type of verifications. Nobody can basically just come and add the rest of the keys there. So that's how the platform firmware turn from the setup mode to user mode, right? So that's the role of a platform key. Similarly, the KEC or key exchange key, this is typically stands for the key for the OS. That means the platform owner basically creates multiple OS or multiple NOS on top of the platform, and each NOS has a different sets of key. Basically, it establishes the trust relationship between the OS and the UP firmware. Now, to enroll the platform key, the platform key typically here in this picture shown that sign the platform KK key by the platform PK. Okay, now PK is already enrolled at the initial time, and the KK can be enrolled at any time, but the enrollment is required as signing of those keys. And the UP firmware will verify authenticity integrity of that KEC, and if it is validated, then it will basically add into the UP database. Now, KEC is further basically gives a response, takes an accountability of rest of the keys. Now, the platform owner established the ownership relationship with the hardware. Then the owner can add any key in the signature key database. Typically, we talk about mostly the secure boot key. So it depends on the one or more than one keys, depending on how the owner wants to establish. So those keys are kept into the secure signature key list. And also the UP also maintains the forbidden key list, that if there is anything the owner decides, or if there is any NOS keys got compromised, that key can be put into the forbidden key list, so that the system disallow the booting of such images. This normally happens in the when the key gets compromised. So on top of these platform key, K exchange keys, signature database, forbidden keys.
Sorry, can I ask a question here?
Yeah.
Okay. So I think you mentioned KEK is for the North, and then you have another secure DP. What's the difference between the KEK and DP?
Yeah. So KK basically used this is all the key hierarchical relationship. Okay, you can say that PK is ultimately account authorizer. The PK can enable any modification in the UPDB, but KK we created a intermediated key, because PK is a root of trust. You don't bring every time under the use. Then there is a sub PK kind of like a non-specific key. Now, what the responsibility of this key is, anything we modify in the signature database list or a forbidden database list. Okay, the KK key is used as an authorizer. So it authorizes any modification on the signature data. Say, for example, if you want to remove the key from that signature database, then we need a key to be formed such a way that it is signed with the KK key and sent it to the UP firmware. Now UP firmware basically has the public key of the KK and verify the changes which comes to the UP firmware, and it takes an action according to that. In this case, insert a key to the UP database, something like that.
Yeah, let me ask this question, right? So let's say, I don't know if the energy is good or not, but let's say, we have a Windows and Linux, right? So the Windows have its own KK1 and the Linux have a KK2, right? So let's say if Windows vendor, they decide to add a DB key in there using its Windows KK1 to sign it. Can the Linux, remove it, using its own KK key, like KK2, or it has to be removed using the KK1?
No, you see, that's what. If you want to update or change or remove the KK key, it requires a platform key to be authorized.
No. I mean not remove the KK key. I mean, to add this, forbidden key, the DB keys.
Yeah. So okay, I think yes, that needs authorization on KK. Say for example, there is a multiple KK, KK1 and KK2. Okay, ideally, why do we have a multiple KK? Okay, you have a multiple NOS or OS kit, right? Now, this OS kit can come from the same vendor or a different vendor. So basically, it gives a flexibility of or isolation there. So when I mean multiple or OS, that the private key of that OS depends to that particular vendor or business unit or a group, right? Now they don't give that private key accessibility to the other group. In that case, they I if the OS2 wants to add a key or remove a key, right? They need a key to the KK2 to update. But if they have a KK1 private key, your question, then the KK2 can also update it, right? So
okay, so you mean that adding
yeah, basically
the DB or removing as long as it's signed, then it's fine. It doesn't matter which key you use it to sign, right? So and you can remove a DB key using a different KK key than the key that used to sign and add that key, right? So, okay.
Yeah. But the point here is, so okay, I have a section there. Let's go into that. Actually, these keys are asymmetric keys, right? When we create these keys, there will be a pair of keys, private key and a public key. Okay. Now the private key we normally use for signing purpose, and the public key we enroll into the system for a verifying purpose. So, but when we are doing a certain operations like in a modification on or a deletion of the DB, you need to have an access to the private key. Normally, a group 1 will not have access to the group 2's private key. So that's how it basically isolates their operations on the DB, right? So let me move.
Okay, got it. Thanks.
Sachin, I have one question. Suppose that platform and NOS from the same vendor, do we need to still maintain the both keys?
It's optional. Basically, the spec says an optional. You can use the same PK as a KK also. The PK has an ultimate accessibility that it can change not only K, it can go and change the DB also.
Okay, that key exchange key is only for NOS, or what about that firmware upgrade packages?
It really doesn't mean that NOS. It's a kind of a guidelines that when you created a key, you basically organize those keys such a way that it won't basically interact or collide its roles and responsibility, right? Now, in this case, KEC basically it's up to the platform owner it whether they can use it or it's an optional or they can have a multiple keys. It's up to them how they want to organize. The idea crux between here is that the authorization of that key is required to do the any operation on the signature database list.
Okay.
Right.
Thanks.
So it's kind of an optional. If the you are right, if the system owner are same, and it becomes a redundant there actually. Uh, and the system is a basically closed system kind where actually the hardware and software, firmware, all three entity comes from the same, then they can use the common key. But ultimately, but that should be authorizer for DB signature database and the forbidden database.
Okay, thanks.
Yeah. So some important things like so we are talking about next is an authenticated variable, right? So in UP, these all the keys we call it as an UEFI variables. Okay. Now it can be hashes, or it can be OpenSSL generated key, or a digital certificate, or it can be some flag or variables like a secure boot mode or all those things. So those all are called as an UEFI variables, right? So now some implementation of UEFI may kept them as a unsigned. They don't require to be signed, and so it depends on the how it is implemented. But the specification basically says for protection of these UEFI variable, use a mechanism of a signing and verifying model. Now that's where these authenticated variables comes into picture. The authenticated variables are nothing but extra layer or additional layers on the top of the UP layer, UP variables, where the UP variables are signed, and when it is basically accessed in the system, like in a PK or KK, whenever we want to show or access or modify, we need an authenticated variable to do that. Basically, we have an example below. This authenticated variable is a extra layer where it carries the signature of that operations as well as the data, so that UP firmware can validate and establish the trust source, then update the database. That way, it is a securely manage the UP management. So authenticative variable basically provides a very protected way of managing the UEFI variables. So now, since we understood some of the basic concept, there are so many other terminologies, but here we try to focus very much functionally for UP key management. So that's what we brought, only the necessary things here. The UEFI key management, basically what it means. So it means that the platform owner generates these keys, generates the authenticated variable, okay, then actually adds or enrolls these keys into the UP system, or he should able to remove the keys from the UP system, and should be able to revoke the keys and dump the keys list. Okay, how it is being done in typically, that's how it is we talk here. We mainly, because every vendor might have a different signing tool, signing infrastructure, and signing policy in their world. Like in Azure, they use a key vault infrastructure to create key and all. But we talk here more standard, like what Linux supports, and others should also support similar way. So here we use OpenSSL. As I mentioned earlier, these UEFI variables are nothing but a symmetric key Asymmetric key means basically when we generate, it will generate a pair of key. One is a public counterpart and one is a private counterpart. Now the private counterpart we normally use for securely, we don't expose them. Public counterpart, basically we share it to the other entity who we can basically yeah, can basically view the content or modify the content. So in that model, the private key we use in the SONiC to sign the certain root bootkit artifacts, such as we have these bootloaders and kernel modules, right? Now, once this protected, right, kernel is protected, the further chain of trust can be established with the additional keys, but the UP specification does not go beyond that. So once you have a very trusted kernel, it's up to the vendor. How they want to. They can basically continue to establish the security on their Docker or their binaries, etc. Now that we don't go beyond there, so we will focus only on the secure boot here. So this is a typical sample of how the OpenSSL creates a key. For example, here I give an example that how PK, KEK, and DB is created. And the minimum is it uses RSA 2048, then SHA of 256, and certificate of type is X509. So outcome of this command is pair of two key. One is this one PK key for the, and other one is a PK cert. The PK key is a private key. If you do, it is kind of a encrypted key. If you dump it, it's just a number of some hex numbers, which is generated based on the entropy of the system and all. And PK cert is a public certificate which also embeds the public key. So yeah, so this is sample here we create, and we got the pair of key here. Then how do we generate an authenticated variable for this one? So these basically act as an UEFI variables here. Now we are going to be make it as an authenticated variable. How do we do that actually? So there are tools available for doing that. For example, in this case, OpenSSL, as well as there is a EFI tools, which provides a certain utilities, right? So once we have a keys generated here, the keys public part is basically kind of in a format, PEM format. Okay, and when we are converting them into the ultimately in the authenticated model, we need to basically convert them into the DR format, then convert into the ESL format. ESL means a signature list format. Then once we have a signature list, then basically use this command to sign PK private key, and use the PK public cert and generate a PK auth. Now, this authenticated variable happens outside of the system, not in the system. It happens in the secure, in the signing infrastructure or signing services, or some outside Linux machines where these all are available, right? So if you look at this example, the main crux here is that we are signing for a PK authenticated variable. We are signing with it's a self-signed. So we are signing with the PK private key. And for a KK authenticated variable, we sign with the PK. And for a DB authenticated variable, we sign with the KK. So basically this is the example for this, the picture shown here. The PK is a self-signed, and KK is signed with the PK, and and the DB updates signs with the KEK. Now, once we generated a authenticated variable, DB auth, right? Then there is a enrollment process. Actually, we copy this authenticated variable on the system. Then now we need a interface or a CLI, some sort of a CLI, which can basically transfer this authenticated variable to the UP permit. Now, the NOS is just a transporter. Yeah, it might take some additional checks and balances, but the ultimate verifications or authenticity integrity check has been done in the UEFI firmware itself, right? So here what we talk is that actually for a PK or for we copy the authenticated variable, then we invoke a CLI which will transport this data to the UP firmware. Then the UP firmware checks the trust source and integrity authenticated variable and enrolls into the UP database. The system requires a reboot, typically after modification, right? It goes for a reboot so that to activate the new key database, the updated key database. And in the similar principle, we can create a removal of key. Here, the example also mentioned for the removal of key. Okay, same thing. We have a keys. Say, for example, for a removal of key, we read the keys from the key database. This happens from the system. We read it, then get a signature data list from the DB. And say, for example, this has a 3 keys, and we want to remove the one of the keys. For example, here in this case is we want to remove the second key. Okay. Now get the key list, convert into the dir format, and then convert into the ESL format. When we convert into the ESL format, the single red key dump will be converted into the individual key, like key 1, key 2, key 3. Then remove that second key and use and then create a concatenation of a first and third key, which will act as a new key, and then sign it. So we signing it with since we are updating the DB or removing the content from the DB, we sign it from the KEK here and generate a new authenticated variable, and which should be transferred to the system. Now the public counterpart of the KEK is already available in the system or UP database. It will validate this authenticated variable and take an action of updating or remove the content. So there are many ways. This is one of the utilities. There are some other tools also available, like EFI, readware and updateware. This also provides a certain level of way to change that. Now, similarly, the revoke key. The revoking key is basically, it is if you see here, revoking keys from the UP database is done when the previously trusted key is no longer trustworthy. So when this action is taken when the key security has been compromised. So in that case, what we do, we will basically revoke this key and put that key into the forbidden key list. That means any image signed with that particular key is permanently forbidden to boot on that system. The show keys are kind of dumping the key list from the UPDB. So it will basically in the system where whatever the UP keys are there, all these keys are there. If somebody wants to see that, actually the CLI is required to dump them. Now, so we talked about mostly on the how the key management is done. Now, what is required from the SONiC side, right? Now, as I said, there are multiple way to implement this one. So in the UP, most probably the most of the standard Linux, like including Debian distribution, Red Hat, Fedora, they used this similar model there. And but there is also some other like a mock manager and shim. These are kind of mainly created for PC based, where actually you need a physical access of the box and do that. But when the network, right, in the operational network, there is a huge number of network and has to be managed remotely. There's some sort of a remote management is required. So that is where actually SONiC plays. We need an API which is exposed to the SONiC. So here we created a kind of a sample, the SONiC will create a plugin model where it will basically exposes the mode as well as the get variable and set variable. Okay. Now every UP vendor, the platform vendor, basically they can implement the way of getting those, right? So I have taken the OVM map here again. In OVM map, basically normally we use as tools like EFI tools. Here is the stack of a OVM map. OVM map here, this is the OVM map permit. All the UP database is exposed to the kernel through the runtime services. Now, kernel has already standard drivers and all for which comes with the EFI kernel EFI subsystem, which access these runtime services and exposes the entries to the Linux user space via EFI varfs. Now, this EFI varfs is a kind of a file system which will basically exposes all the UP variable like a file, so that the user can access operate them on as a file. And the contents are so even though it's a file, it's basically a bunch of a hex dump of a file. Some information like certificate informations can be passed. That's where the EF5 tools comes handy. There are already read wires and update wires, which we knows how to parse and display the some of the content. So that has been shown here, that EFI read wires and show. Now, idea is that in this OEM based system, then actually we integrate this readware and updateware in the SONiC plugin, like a get variable and set variable, which takes a variable name and value. For a set variable name or value. The value is nothing but the auth file content here, whichever we created, like in this case, the content of auth file, right? Now, how this file looks like, this is where it requires an mounting the F5RFS onto this particular sysfs entry. Now, if you see here, this will be looked as a file, like for a PK, PKGID, KEK, DB, DBX. So for example, if the DB has a multiple keys, you will basically see the single key, but it will be in the signature list format. The hex dump is completely contained with the key 1, key 2, key 3 is hex dump with a certain header. Right now, SONiC CLI basically provides this plugin provides a high level, and the implementation, like in the OEM app, can change for platform to platform depending on how the implementation done by the platform UP parameter. And at the high level, the SONiC CLI commands looks like similar, like show platform security UP variable all, which will dump all the keys, or we can specify the PK, KEK, DB, DBX for a dump or show to display purpose. So this will underneath uses this plugin to go and do the query on the get variable, passing the PK or variable name. And that will basically interact with this EFI tools. And from the EFI tools, it fetches the information like a file and decode and display the content of it actually. So similarly for config CLIs, these are the config CLIs where we can, like EFI variable update, PK, KK, DB, DBX. So this update basically to make a modifications. So if you look at this one PK, what it does, it just transport the content from what the auth file to transfer to the UP firmware. Now, security built in the auth file, because since it is in the auth file, since it is signed by and privately done and transferred to the system, and verification is done by the UP firmware and update the DB. between the SONiC CLIs or platform implementation act like a transporting this information from user space to the UP permit. And we also can we implement some sort of test automations using a SONiC management by having a predefined test authenticated variable. Using that, we can test adding, removing, deleting those keys. Normally it won't applicable for PK because if if you are removing a PK, it's basically the system will turn into platform ownership to the non-ownership mode. It is not good for the security purpose. Yeah, this is the overall the HLD talks about the UEFI key management. If there is any questions or anything, I can take it up now.
So okay, sure. I think what is actually the contribution here, for example, I think you propose some UEFI based Python APIs, right? Where is that contributed to? Is that going to the SONiC platform common, or where do you plan contribute?
Yeah, so as I said today, right, vendor can implement it their own based on the Linux, right?
Yeah.
But that implementation change from vendor to vendor. Now there should be an infrastructure where vendor can implement their part, and SONiC can consume as a common layer. So this UP base class will go like in a plugin class, mostly in the SONiC SONiC dash utilities common code, and it basically defines what the input argument and what are the error types. So here error types have to be captured. The error type is typically comes from the EFI protocol. I have to mention that actually. I'll update them once. Even I'm at this time completely unaware about what all the EFI variables we support. They are on a certain different type of a failure, right? So that has to be brought in. But it is available in the specification what EFI errors and all. That's how actually this base class will map that if there is certain failure, the EFI permit error will be turned into some sort of a common error, and also if it is required syslogging certain information that can be added in the common class. The plan is put in the common place where source other plugins are there, like a chassis plugins or other various plugins are there, and put and give a platform vendor to way to implement the their specific access method.
Okay, so this, if I understand, this UFI base should be in the platform common to define the, the common API, right, to access those variables. I think the one thing I didn't, the section, 2.5, right? So it seems there is already some implementations there, right? So on this I mean, would you be able to provide the so where to have this OVMF based Linux implementation? I mean, I assume, okay, let me put it this way, right? So, if we have this, those common Python API defined, then I guess one of the implementation will be using the OVMF implementation, right? So based on the Linux implementation. So where do we put that in? Because I think maybe I think the different platform they have a different way to access the UFI variables, but it seems like OVM based platform is a common, right? So maybe that's also a common work that people can leverage. Or
I got disconnected. Can you repeat?
Oh, okay. I mean, this OVM with based Linux implementation, where do we plan to provide that implementation? Is also in the platform common, or yeah, I'm trying to understand that.
This is this OVMF implementation, right?
Yeah,
This implementation comes outside of the platform common. Yeah, but it can be a multiple vendor use the same similar model. Uh,
yeah.
yeah, yeah, right. Most of them, I agree that if you look at that any distribution, most of them uses this model. So that means this
Yeah,
becomes a kind of a common.
yeah,
But having said that, it's still in a platform specific because some other platform may be accessing them in a completely different way, right?
yeah.
So yeah, that is something like if the base if it can be make it as a default plugin versus specific plugin because that can be done. But at this time, I feel
Okay.
that actually um, it's a kind of a platform specific, and we can make a generic infrastructure for various platform by keeping it as a utilities in the SONiC. SONiC SONiC utility directory or something like that. That can be done actually.
Yeah. So maybe this part I still don't quite get. So what is so okay, so for example, I think the plugin class, I think it's clear you will define that the SONiC platform command to define that class, right? So provide API. But what about this OVM with implementation? Do you plan to implement that? Or yeah, what is this section 5.2 means here?
Okay. So here explicitly mentioned to avoid a confusion that we use a OVMF firmware implementation. But if you look at the Cisco's implementation, it is basically same that OVMF implementation. So
Okay.
we are going to contribute all the integration of this one as part of the Cisco, not necessarily for OVMF. But do we
Mhm.
have a emulation? SONiC has a virtual machine. So I'm not sure whether it's a OVMF based or what it is. If it is there, that can be used for that virtual machine also. I remember NVIDIA was saying secure boot implementation on the virtual machine. Uh, if that is so, I feel that that would be a based on this Diana Core OEMF BIOS implementation. So what I'm
Okay. So but okay. So I guess so when the virtual machine is a different, maybe it's a different conversation. It's about, okay, so can we, if we provide this section 5.1 to 5.2, is there a way that we can validate everything works, right? So then maybe we can not on the real hardware platform, but based on a virtual machine, we can also validate that. Right? So I feel like that may be a different conversation, right? So is that correct, or is that my understanding correct? Okay. Am I audible, or?
Yeah, I can hear
Yeah,
you.
yeah, you
Hey,
are. I
Sachin.
guess he got disconnected, I guess.
Oh, okay, okay,
got
okay.
disconnected. Yeah.
Maybe you go ahead and leave your comments in the HRD.
Come again?
Nicolas
Sorry.
addressed. Oh, Sachin. Okay.
Hey, Sachin, your document sharing is gone. Probably we lost you briefly.
Yeah.
I have a very quick question. This whole HLD provides a template for anybody to add their own keys and load their own self-signed images. In the whole process, where would I filter an unauthorized user or like a rogue user follow the same steps and then load their own images.
Okay.
In
good
this
point.
whole process, where would I stop that?
Okay, good point. So that is what the see when actually say for example, let's take a specific example of a Microsoft case here, right? Say Microsoft received the hardware, right? Now, once they receive the hardware, they have to establish the ownership of that hardware by putting the platform key. Now there is a different methods here. Okay, one, the hardware vendor supplier basically takes a Microsoft's platform key in their supply chain and add it and lock the system and send it, so that in the transit time nobody can basically uh, take a ownership or change the UP database, right? Only the Microsoft has the private key of that platform PK. So they are the only the person they can update the rest of the keys. So any rogue user cannot update, because when they try to update, basically the system will reject. Okay, there is one way. Or some vendor basically keeps this platform key PK also in empty, and somehow they have to securely transfer. But once it is in the Microsoft premises, the initial provisioning of the system micro will be done through Microsoft enabling adding the PK. So the system is considered as a Microsoft will not able to add a PK if already somebody enrolled the PK. That means they can check the PK is already there, or the system is already moved, the UP parameter is already moved from the setup to user mode. So they can do the check and balances before basically turning it up. So and UP firmware accept the rest of the keys only when the PK, only after the PK is enrolled. Until then it won't accept. And it accept the PK only in the setup mode. It doesn't accept the PK for unauthorized PK from an user mode. That's how the protection of a supply chain is done.
Touching, but okay, it's Eddie from NVIDIA. Okay, so the regular way to update UEFI keys is through UEFI shell. And then it's good practice to have a special password to protect access to UEFI shell. Now you are actually exposing the access to UEFI database from SONiC, right? Okay, so we are doing our security is a bit weaker, right? So no additional level of security here, and anyone with access to SONiC CLI can generate new DB key to sign a Linux kernel, to read the KEC, to sign new DB public key, and to enroll it, right? And that it will work, right?
No, that is what actually we mentioned here, authenticated variable. And also we mentioned how your UP firmware is exposing CLI. See, what SONiC is doing today.
If you're sharing the document, it is not visible. Any document or referring to any text.
Okay.
Are you sharing anything?
I was
you need to reshare the document. Yeah, I think it got.
Okay. Yeah, that's a valid point, and that's what this authenticated variable mechanism avoids. So that's what in the initially I told how your UP permit. Okay, let me get it. Yeah, authentic variable is provided. Okay, thing is on the PC kind of a model, right? Normally the UP interface exposed through the BIOS menu or some sort of a console shell, right? You would be, doesn't require remote access. It has to be physically available. Okay. Now, but that doesn't scale for a large scale. So we cannot do individual card or devices to get into the console and do that. So here two things involved. Now, how your UP firmware is implemented. In the case of OVMF, they support the authenticated variable. So authenticated variable means until, see, the root of trust here is a platform PK. So when I gave an example that, for example, hardware vendor, when he supplies the system to Microsoft, he will enroll the Microsoft's PK and lock the system and hand over to the Microsoft. Now, using a SONiC CLI, if anybody wants to enroll the keys, for example, enroll their own NOS key, they cannot do that because they need a private PK of that. Right now, this private PK it's not exposed, not supposed to be exposed to the public. That's why it is a private.
Sachin, but your DB key is signed with KEK, right? And you can read KEK with your CLI, right? So
Yeah.
all you need.
Yeah,
Wait.
here again, KEK, see, UPDB contains only the public part, not the private key. So
Okay, right,
it
right.
contains only public keys which are exposed. Definitely public keys are exposed from the trustworthy like a Microsoft through their PKI server or some key server, right? Now, the system owner is supposed to enroll only public key, and private key, keeping them secretly is some sort of the platform owner's responsibility.
Okay,
Right.
okay. So what prevent me from replacing all the keys? Okay, I have access to CLI. Okay, SONiC CLI with your exposure of all keys starting from PK. Okay, to CLI, I generate everything and replace everything. PK, KEG, DBs, everything. Okay, without any additional password, right? Just with access to SONiC CLI.
Yeah. So, okay. In that case, it's a kind of a logistic here. What Cisco is trying to do with the Microsoft, that actually when Cisco supplies the hardware, our supply chain will enroll the Microsoft PK, so that if you catch hold or any row person catch hold, the system is locked with the Microsoft's PK. Now he cannot enroll any key using a CLI. When he try to do, the CLI respond back with the error saying that it is unauthorized key.
But platform key can be replaced any time in UEFI DB, right? So it is not to lock
Yeah.
it in UEFI DB. Yeah, it is not standard way. Yeah, UEFI works.
I think okay. Again, I'm saying. So you see that is what, right? This is depends on how best the UP variable is implemented, right? Or UEFI parameter is implemented, right? Now, if there is a problem in a UP firmware that accepts any kind of a key, then that's a security hole of that firmware, right? In the OEMF, if this is it has been set for an authenticated variable model, right? Then it cannot accept any key. It accepts only the signed key. Okay, and even answering your questions, OVMF, right? See, today already
Sachin, to clarify, right, Sachin, in order to change the platform key, won't you need to actually have the private key of the platform and then sign it and then do it?
Yeah. That I mentioned.
Yeah, so basically the private key is not available to everybody, right? That's only available to the platform owner. And that was, I guess the question was, how is the security maintained in this model?
Confusion this private key, okay. The private keys are not exposed. If the private key got compromised, then actually system got compromised, right? So it is not exposed, and it is same thing as a password. If a password is compromised, then again you get an access to the system DB.
Yes, of course. But okay, additional password on entry to UEFI shell creates additional firewall, right? Okay, so not anybody, okay, having access to SONiC CLI should be able to replace to change actually secure boot sequence, right? And to replace all keys, UEFI keys. It is my concern. Okay, so we are easing the access to UEFI keys and kind of shooting ourselves in the foot, right? Okay, from security point of view.
Yeah,
But
but
these are
actually,
public keys, right?
here,
Aren't
like,
these
yeah, go ahead.
aren't these public keys that we are displaying here?
Come again. Yeah, public keys are displayed here.
These are all
Yeah.
public keys we are displaying here, right? We are not displaying any private
No, it's
key or
only
secret
public
there.
keys. Public key are exposed. Yeah, only public
Yeah,
key.
so then
But maybe
why
maybe
is
I
there
have
a security concern?
but maybe I
Yeah.
have this question. So the mount command, you know, if you are root user, you know, nobody can prevent you from running the mount command, right? So I'm not sure, you know, what is
So that is what I mentioned. The CLI is not a security here. Okay, see, the security is built in the authenticated variable since you are signing it, right? And the UP permit, which basically implementation goes to the implementation how UP permit is implemented, which basically only accept the authenticated variable if it is a signed and it is a you know authenticable and verifiable, right?
Yeah, but
The CLI,
authenticated variable assigned with which key? Where is root of trust here?
the platform key, every key has authenticated variable. Like every key is being signed and enrolled in the system. The UP permit will basically verify and then only accept this, those keys.
But again, if I replace platform key, right? Okay, I generate new pair, okay, and put here public key and using private key to sign all new generated, okay, no problem. I just replaced everything. So it is just about additional password level, okay? It's additional level of security that we probably have today when we are doing it from UEFI shell. And now actually the whole process is exposed to everyone with access to SONiC CLI.
Okay, how do you enroll the private? How do you enroll the platform key? I'm saying I have blocked the platform key enrollment by already enrolling it into the supply chain. It won't accept your private key, or sorry, it don't accept your PK public key until it is signed with which is already available, previously enrolled in the supply chain.
Yeah, but it's self-signed, right? PK, it's self-signed. You don't have any other key, okay, root of trust to check, to validate the signature of PK.
No, but how? It's okay.
The issue here is the self-signed image, and you provide the infra to make everything happen, even for a.
Yeah, it's self-signed, right? Okay, so I can generate new one and to put here, right?
I see. Even though self-signed, how do you get in a private? You need a private key to update. See, I'm saying I already enrolled the PK. My ownership is already added it here. Now, if I don't share you my private key to you, how do you enroll?
Yeah, so
That
I
is
think
not
Eddie, what Sachin is saying is like in the during the enrollment, right? When you receive the hardware and then when you become the owner, so that's either it has been already enrolled by the machine vendor, the hardware vendor, or the as you as a platform owner receives, and then as part of that enrollment or enablement, so they insert the key for the very first time because there was no key present, and then once they install and lock the key, after that point, even if you have access to the CLI, it doesn't mean you can do whatever you want. So only authorized users are allowed to make changes. So then that authorized users is protected with the private key that they have stored it in their own database. That's not in the system. or on the
Okay,
platform?
I'm not aware, yeah, of the way to lock platform key, okay, to avoid its replacement in UEFI DB. Maybe I need to read more
Okay, I
about
think
authenticated variable, but PK on
no, I
today's
think
systems, okay, can be replaced. Yeah.
yeah, I think Sachin, I think I kind of understand a point a little bit. So in our systems, like Cisco systems, you cannot do that, right? Because we have a hardware-based root of trust. So if you don't, meaning that the platform
we
itself
cannot,
integrates.
yeah, we cannot do that. Only reason is hardware root of trust comes again at different level. This is a UP root of trust, and
Yeah, so I
once
think
that's
the
that is
concern,
once
Sachin, is that if UFI allows you to change the platform key through a shell, then then we are kind of allowing somebody to change the platform key from the SONiC. So maybe something we can
no.
just discuss
See,
and no.
the point here is even Cisco cannot change. Say, for example, Microsoft shared only the public part of their key. Okay, Cisco manufacturing at the time, the firmware is in the setup mode. Okay, Cisco can enroll it. Once it is enrolled, the firmware automatically locks it. That's how the firmware is designed. Okay, now the public key is already inside a system. The owner of the platform is a Microsoft, and now if Cisco want to change, Cisco cannot. Cisco needs a Microsoft private key to make the changes in the platform, even for the PK. Right now, that is how the ownership of the hardware becomes the root of trust here. Okay,
Okay,
now
correct. So yeah, the platform key. So basically, the new key that you are providing has also got to be signed by the same
exactly,
private key of the PK. Yeah. Okay. Then
yeah,
you are not. Then you cannot. But I don't know how this works for so like I say,
yeah,
standard off-the-shelf box, right?
yeah. That is how
That
actually.
works.
Then actually, if their UP permer has the gap, then they should not expose or implement. See, that's what CLI, SONiC CLI is just a plugin. Okay, now the platform vendor
Right.
like Cisco knows how to access and how to protect their UP. That's why we will expose. Now, if other vendors they feel that okay, that firmware is not enough to not that secure for the runtime CLI, and it required only for the shell or console access, that is something. Then actually they don't implement it.
Yeah, that gives them the flexibility, right? So they don't implement the set variable there.
Correct.
Yeah.
It's a trade-off between security and flexibility and maybe automation and large scale.
Yeah.
Right.
Yeah.
Agree.
But
Agree.
point here is when you are managing the large scale systems, right? You cannot depend on the shell. So that's where the UP permer has to become a more and more stronger. I think that is where these authenticated variables and other things comes into picture.
No doubt here. Okay, we just agree. Okay, we need to agree that there is some trade-off here. Okay, security versus flexibility, and large-scale support.
Yeah, and I think I think more and more we are security with obscurity is not really considered security anymore, right? So we think that it is that still somebody could get access to UFI shell, and if you could break your system, then that's a security hole
Yeah.
anyway.
Yeah. Password also can. Yeah.
Yeah.
It's just additional barrier, okay, for someone,
Actually,
who
I think,
should not have access to UEFI keys.
Yeah.
I
Point
think
here is
that's where this is given enough flexibility.
yeah. In this implementation, though the CLI access is there, only platform owner can make the changes. Since the PK is enrolled, the public part of the PK is enrolled, and the UP firmware is locked by moving a setup mode to user mode. Now to come back to the user setup mode again or delete the PK, only Microsoft can do it because Microsoft PK is already there.
Yeah.
Now,
Okay, Sachin, is it some standard capability of locking PK in UEFI DB, or it is your addition to UEFI?
it's a standard. If you look at I think OVMF has defined a document for that. I think you can look for setup mode, user mode, all those comes from there. But Cisco has a different implementation, some sort of some more protection. But I think OVMF is self-sufficient actually. Yeah, it is there in the spec actually. Anybody can refer.
And then another thing that Sachin mentioned was, I think the platform key is not used that frequently. So here, most of your operations will be done using the KEK. So like PK is more of a master key. So you use it like when the things are compromised. Otherwise, like a lot of your day-to-day operations or whenever you are enrolling, allowing new NOS to be run on that system. So that time, so most of your operations are based on the KEK. And then again, these are only the public part of the keys are in the database. All the private keys are in your own secure domain.
Right? It's clear. It's clear.
Yeah, let me add some points here. So the key management comes from the actually like a Microsoft kind of a vendor, right? They have their own Azure Vault key system. Okay, now that is a separate entity from the secure boot. The key management accessibility from the infrastructure itself is well protected. So they can say that the platform key is a kind of a root of trust. Only certain level of people are able to access the platform keys in the Microsoft premises, right? Not every engineers or dev engineers or release engineer can access. It's only a trust, like an executive level or something, and they can release this key only in the certain. Some sort of a policy can be set on the accessibility, right? So in Cisco, that's why platform keys are very secure. It won't be accessible for everyone, and KEK is a kind of a next level subordinate. So we have a very strict policy set on that only certain people can access the KEK private key. And yeah, then actually dev keys and all the. So you guys also have a NVIDIA already published a method, right, where actually production key versus production signing versus dev signing. It's based on the similar principle that dev signing happens through generic keys and the production signing happens with release key. Yeah, so that is a kind of a policy the vendor platform owner will set according to their security measures.
Okay, thank you.
Okay, thank you, folks. I think we are running out of the time. So if you guys still have any comments, feel free to leave your comments in the HRD. And also, if you want to be the reviewer, just also leave comments or let me know. So thank you, folks. See you next week.
Thank you, Andrew. Thank you, everyone.